Good afternoon, depending where you are. I will speak about health protection using clay minerals, and this is a study that was performed during 4 or 5 years by several students, second and first degree, in projects, in short projects. And due to that, there is a lack of consistency in the methods. But in the end, we gathered a lot of information about how to use clay-based technologies for the removal of BPA and BPS. And the lecture will speak, at the beginning, I will speak about EDCs, why are those considered health hazards. And in this experiments, we'll present two approaches on how can clay contribute to EDC removals from water, and those are absorption and photodegradation. I must mention that it is impossible to deduce from one pollutant to the other and from one solvent to the other, because small differences in the molecules can yield a large difference in the results. And we will see it in these different cases. In general, when we're talking about water, we know that freshwater sources are limited, and sewage from main sources contain contaminants and pollutants that in some cases are not fully removed by conventional water treatment. And for example, hormones in pharmaceuticals, in some cases, those are not so much of an issue because the concentration is too low. But in the case of endocrine disruptive compounds, EDCs, we know already that the consumption of such pollutants, even at low concentration, can be dangerous to health because they mimic hormones and they block them. Two widely used EDCs are BPA and BPS, and they are coming from the plastic industry. And there is an increased awareness, especially for BPA, less for BPS, but in most cases, you can find them both. And in water, in some sources, the concentration may reach even 30 or 50 ppb. And the reason is that even though those are biodegradable, wastewater treatment plants are only partially effective in removing them. That means that researchers agree that the removal of them from water requires urgent attention. Clays were used for EDC removals and are used in at least research. There are three approaches: biological degradation, absorption, and advanced oxidation processes. In biological degradation, we can connect enzymes or fungi to clays in order to get a surface that is biologically active. And in absorption, we can specifically engineer a clay-based solvent that is effective to remove the pollutants. And in AOP, we can prepare clay-based catalysts that are also and test them and expecting that those will be effective. In this study, we will present experiments on the two latter techniques, absorption and photodegradation. Let's start with absorption. A lot of absorption media were tested for bisphenol molecules. However, there are not enough organized results except maybe for activated carbon. Absorption matrices based on clay minerals were tested since the beginning of the 21st century, mostly for BPA, less for BPS. Several pillar and organoclays were tested. In most cases, quaternary ammonium, large organocations, but also pi-pi interactions were exploited for this matter, based pyridinium surfactants or other aromatic cations based. That's what we are going to show. We're going to show an aromatic organocation based on the pre-absorption of vitamin by B1 thiamine on montmorillonite. This organoclay, specifically this organoclay, was found to be very effective on the removal of phenol in aqueous solution, and we will try to test it in BPA and BPS. So let's take a look at the results in batch experiments, absorption isotopes. At the beginning, we tested raw clay minerals, and we started with minerals that we know that have binding sites to neutral molecules, like halloysite and sepiolite. Unfortunately, what we saw is that there is no absorption of BPA on neither halloysite nor sepiolite, and of course, also in montmorillonite. Montmorillonite has no binding sites to neutral molecules, so it's not expected to absorb. When we started modifying the montmorillonite by using a PAH, polyaromatic heterocycle like berberine, then we got some absorption, some partition between the absorbing matrix and the solution. But absorbing BPA on B1 montmorillonite was a lot more effective. We get complete removal up to almost 0.15 millimole per grams, and after that, a diagonal line that means a partition between the matrix and the sorbent. That means that at high concentration, we still have increased removal, even though we have some BPA remaining in the solution. At low concentration, we have complete removal. For BPS, the results are less exciting because we have still complete removal at low concentration, but we get saturation, and we at higher concentration, everything above the complete removal remains almost in solution. In order to get the things in proportion, I would like you to take a look at the absorption to phenol, because we will see that if we compare it with phenol, we get that the absorption of BPA it's low, relatively low. But the reason of that is that this specific sorbent is really very effective in the case of phenol. So we will have to deal with what the absorption of BPA and BPS mean. We tested also some absorption models, and we started on the results of the absorption of BPA and BPS on B1 montmorillonite, and we started with Langmuir equation and with a dual model that is a combination of Langmuir equation and a partition part. And we got that the Langmuir model does not fit very well to BPA absorption, but that's fit quite well to BPS absorption because it reaches saturation, and that's what we get from the Langmuir model. The dual mode model, it's very good in fitting the results to the BPA, and it also has some improvement in the BPS. And if we summarize those results in the table, we can see here that the Langmuir equation has a bad fit to BPA, but the dual model fits very well. And for BPS, both of them have some quite a good fit. That means that we can use the dual mode model to calculate the amounts of BPA and BPS absorbed very effectively. The next step was to test column experiment. We took the pollutant. In this case, it's a color, but it's not only to see it. And we had a peristaltic pump, and we passed the solution through a column, and we collected what is passing through, and we measured the concentration in what is passing through. And we have the pore volumes through the column, and these experiments that are known as breakthrough experiments are performed not with all clay or organoclay, but with a mixture of organoclay or clay and sand. And the reason that we add sand is that the hydraulic conductivity of the clay and organoclay is very low. And let's see what we got, which results we got from those experiments. We can see that the clay in the sand, with the sand, does not absorb BPA. That means we get that the concentration is the full initial concentration after 1.5 or 2 pore volumes. When we do it with the columns with B1 montmorillonite, then we get about 14 pore volumes of complete removal. And after that, a slight increase that in the end, after 20 pore volumes, we get that the column reaches complete saturation. In BPS, the results are more complicated because we see that even in the clay, we get we get some removal. That means the results are not as in BPA. In B1 montmorillonite, the results are also complicated. We get a kind of increase all the way after 3 or 4 volumes, the BPS start leaking, and all the difference between the BPS and the BPA can be ascribed to the fact that the BPS is a lot more hydrophilic than BPA, and due to that, it does not bind to the hydrophobic surface of the B1 montmorillonite so well. And in order to remove BPS, if we want to do it by absorption, we need to try to find something that might work better. By the way, this breakthrough results is very similar to what Bill found for quaternary ammonium organoclase at the beginning of the 21st century. So the interpretation is that BPA and BPS both do not absorb to clay, and thiamine montmorillonite is very effective, especially for BPA, less for BPS. And we assume, or we consider, that the difference is that the solubility of BPS is 4-fold that of BPA. Let's speak about the second technology, advanced oxidation processes. And I'm quoting for SSWM website. Advanced organic oxidation processes are a set of a combination of technologies that deal with trying to degrade toxic organic compounds, and in general, they involve a series of procedures. But the general idea, if I'm taking a picture from the same site, is that the AOPs form oxidative agents that attack the toxic pollutants and form from them biodegradable compounds that with time, and we expect short time, dissolve or degrade completely to CO2 and water, what we call a complete mineralization. If I'm trying to show it with another cartoon from my late mentor, Professor Leon Margolis, we have our catalyst, mineral, and we have the acceptor, the pollutant, and then the light hits the catalyst, and the catalyst passes by energy transfer the energy to the pollutant, and the pollutant, due to the surplus of energy, simply fades, degrades, and the catalyst now it's free to do this process again. Of course, that the process apparently is not so simple, and there are a lot of oxidative species that are mentioned in the literature, even though it's very difficult to indeed check them. There are holes and electrons and radicals and hydroxyl radicals. But in the end, what we want to do is to get our pollutant photodegraded and completed and made completely CO2, water, and mineral salts. In our case, we tested what is called heterogeneous photocatalysis. That means light pollutant in solution and catalyst that it's solid suspended particles. In a second stage, we also added hydrogen peroxide in very low concentration in order to try to combine between the processes and get better results. And indeed, as we will see in a few minutes, it gives better results. The main question was, can clays, raw or modified, be effective photocatalysts for BPA or BPS? And we had a gold standard to compare to. It's P25 titanium dioxide. It has several names, several commercial names, but the original was made by Degussa, and it's based on a combination of different phases of titanium dioxide. And it's indeed considered a gold standard because it's very difficult to get the results, the success that this photocatalysis has. There are several studies trying to prepare clay minerals that work well as photocatalysts. As a matter of fact, I think that in most cases we get the best that we can get is something that is similar to P25, and in several cases researchers do not compare, but if they would get that the P25 works maybe better. In this study, we took synthetic montmorillonite because we wanted to avoid impurities, and barazim that was impregnated with titanium dioxide by a procedure that we take that they took from the literature. And in some experiments, we also added a very low concentration, about 60 micromolars of hydrogen peroxide, in order to see if it can help. The catalysts were tested at 2 levels. At the beginning, we used 20 ppms, and after that, we lowered it by 2 orders of magnitude to 0.2 ppm and compared with the P25 gold standard. In order to ensure that we indeed prepare the titanium dioxide barazim, we perform XRF measurements. This is the barazim. You can see the aluminum, the silicon, and the magnesium. No titanium on it. When we measure the XRF of the our modified barazim, then we can see strong peaks, strong XRF peaks of titanium. If we try to say a few words on the degradation kinetics, then we know that the rate of degradation is proportional to the concentration at a certain power. The power can be 0 also. Then we get that there's no proportion. You have also a kinetic coefficient, and as you can see, this is the equation that usually is used to follow up kinetic processes. You can integrate this equation as long as the order is not 1, any number that is not 1. And if you integrate this equation for any number that is not 1, you get this solution where you have the initial concentration, the order, and the kinetic coefficient. The half-life time is a very convenient parameter because it allows you to compare between different processes, even though the order can be completely different. What is the half-life? How long it takes until you get half of the initial concentration? And if you put here inside C above C0 of 1/2, then you get this equation. We can also use the relative concentration, but I will not deal with that here in this case. It's interesting to see that the half-life depends on the initial concentration as long as the order is not 1. When the order is 1, we get something different because the integration of this equation for a power of 1 here, it's very easy, and it yields a half-life time that does not depend on the initial concentration. But I should mention, because there is a lot of information in the literature that it's not widely explained, the half-life time not depend on the initial concentration only for first order processes. If the order is not one, then there is a dependence, and this dependence is very strong. I will try to show. Sorry, I will skip this in order to save some time. I will try to show you by making a kind of virtual experiment. Let's assume that we have a pollutant with an initial concentration of 100 micromolars, and we have 4 catalysts. One works zero order, one half order, one, and one 2. All catalysts, when this is the initial concentration, yield a half-life time of 30 minutes. Again, it's a virtual experiment. It's not something real. After doing that and calculating the kinetic coefficients, let's try to see what will going on at other initial concentrations. At a large concentration, 1000 micromolars, we see that the second order process is very efficient and the zero order process is very inefficient. But on the other hand, if we lower the concentration to 10 micromolars, we see that the second order works very slow, and the zero order removes all the pollutant very fast. That means that the lower the concentration, the lower the order we will be interested in. And if we put it in numbers, for the 100 micromolars, all the processes were 30 minutes half-life time. For the 1000, the zero is 300 and the second is 3, but the other way around for the 10 micromolars. So we will need to decide about the process depending on the concentration of the pollutant in the effluent. In industrial effluents, we might prefer an higher order. But in pharmaceuticals and BPA and BPS that are present at very low concentration, we will need a lower order process because a high order process will not work so well. What was the photodegradation setup? We have a lamp, this one, and from the lamp, this is a fiber optic that goes to a photoreactor, to a Ryonet photoreactor, and inside we have a vessel with the pollutant, a quartz vessel, and a deep probe. This is the cuvette, what you see here, and the fiber optic takes the light back to the spectrometer, and from the spectrometer it goes to the computer, and the computer we can see the process, and we can also of course record it, and after that analyze it. This is the process, and we use UV visual measurements. The benefit is that we can do online monitoring, perform a measurement each 10 seconds. The disadvantage is that we need to use relatively high pollutant concentration. We need 1 ppm at least, or 0.8 ppm, depends on the pollutant, of course, but we need a relatively high concentration. So since we wanted to use UV visible, we first tested if UV visible is a reliable method to measure degradation of BPA and BPS, and we compared UV visual measurements with LCMS measurements, including the analysis of intermediate products. And in the case of BPS, the results are very close one to the other. And the reason is that the intermediate products in BPS disappear very fast. But in the case of BPA, it's quite disappointing because these are the LCMS measurements, the real concentration of BPA, but this is what we measure in BPA. That's completely absurd. At the beginning, we have it seems like we have an increase in the concentration. This is, of course, due to the intermediate products that we could also saw them and measure them in the LCMS. That means that the photodegradation kinetic, if we want to analyze using UV visible, we will need to do it with BPS only. So we use the concentration of 5 ppm, and we test degradation with no catalysis, or with the gold standard P25, or with Barazim, or with our modified Barazim. In some cases, we added low concentration of H2O2, and after that, we lower the concentration of the catalyst by 2 orders of magnitude, and we saw what happened. The calculation procedure was we took the huge amount of measurements that we had, and we performed a procedure known as bootstrap. We extracted 5 sets of 20 random values for each experiment, and we calculated, evaluated using the solver algorithm in Excel, the K and N in order to minimize the difference between the measured results and the calculated results for specific T, for specific time. And after doing that, we took the K and the order and calculated the half-life time. That is the parameter that we will like to compare. Let's see what's going on at high catalyst concentration, 20 ppm. Photolysis with no catalyst takes about a half-life time of 22 minutes, and the order is about 1. By adding only H2O2, we get a lower half-life time, 11 minutes only, and the order changes to 0.8. Titanium dioxide is considerably better. The half-life time goes down to 7 minutes, and the order to 3/4. Barazim and titanium barazim work not so well as P25. The half-life time is about 14 minutes, but take a look at the difference in the order between both. It's interesting. You can see it in the results here, even though the half-life time is similar. But when we add hydrogen peroxide, then we get that the values go down to 8.5 and 7.5 minutes, and the order goes to 0.75. I want to remind you, we want the lower order possible because we are talking about low concentrations. That means that in this case, at this concentration, barazim and modified barazim are not so well as P25, but not so bad. They can match, they can make a fight. Let's take a look what's going on when we lower the concentration to 0.2 ppm. The photolysis and the H2O2 is the same. P25 works not so well as in 20 ppms, it's 10 minutes. Barazim, it's about 12 minutes, similar to the 20 ppm. But take a look at the modified barazim. The half-life time goes down to 10 minutes. And if we add the hydrogen peroxide, we go even to lower values of less than 7 minutes and even 6 minutes, and the order goes down. And that's what we want, to 1/2. That means that at low concentrations, barazim and titanium barazim work better than P25. This concentrates all the results together, but shows more or less the same, that barazim and titanium barazim works very nicely at low concentration. So if I summarize the lecture, we saw that bisphenol, it's a problem to health because it interferes hormonal processes, and in the pursuit of ways to remove such health concerns from water, we would like to present some clay-based materials as either as absorbent or as catalyst for those pollutants. BPA and BPS are not absorbed on raw clays, but B1 montmorillonite absorbs quite nicely BPA. It's interesting to see that the fact that molecules are similar does not say a lot about how effective a removal process will be. And if it works for A, it should work for B. This is an assumption that must be tested. And for the photodegradation process, as we mentioned, we saw that very low concentration of catalysts, clay-based catalysts work very well, especially if we add a low concentration of hydrogen peroxide. And we can get results that are similar to those by P25 commercial titanium dioxide. Those are the students that work on the projects. I want to thank them very much, and the technician in our group. Thank you for listening to the lecture. I will leave some time for questions. Thank you.